Okay, hello to those of you watching. This is the solutions for assignment 7. Number 1, Draw a complete free body diagram for each of the following scenarios. So A skydiver in free fall, include air resistance. So this is my box, this is my skydiver. I'm going to put FD for drag force. It's typically how I denote it. And we have the force of gravity pulling them down. And that was it for part A. Part B, a sled sliding down a hill. So I'm going to draw my box on a bit of an angle, just to show that it's on a hill. The normal force is perpendicular to the hill. Friction would be pointing up, and it is kinetic, because we're told it is sliding. Gravity is always straight down. Part C, a satellite in orbit around Earth. Only have one force, it's gravity. If you drew a satellite in a circular path around Earth and you had the velocity and force drawn like this, well, you are kind of correct. This is a system diagram. This is not free body diagram. So I was a little bit picky about that, unfortunately. I was looking for just a simple free body diagram, not a full system diagram, even if you were correct. I believe if you were correct in your system diagram with all the forces, I may have given you a mark. Depends, I'd have to look back. Lastly, a box being pushed up a ramp. So again, I'm going to just draw this on an angle. Gravity's going straight down. Normal force is perpendicular to the ramp. It is being pushed up a ramp. So I have an applied force going up the ramp. And friction, this time it would be kinetic again, pushing down the ramp. So some quick free body diagrams. Question 1, assignment 7. 2. Well, this whole page, I guess, is a bunch of conceptual problems, but question number 2. Using Newton's first law, this is the law of inertia, describe why a bowling ball and a feather should hit the ground at the same time when they are released from the same height at the same time. Now, this is ignoring air resistance. That's why I said should hit. You know that air resistance will slow the feather down, and then they will not hit the ground at the same time. But so ignoring air resistance, the ball has a greater mass and a greater inertia. Therefore, it takes more force to accelerate it. The feather, or I should say for the feather, the opposite is true. So therefore, it takes less force to accelerate it. Now, the last chunk is that for the ball, it takes more force to accelerate it, and more force of gravity acts on it. For the feather, therefore, it takes less force to accelerate it, and less force of gravity acts on it. These perfectly cancel. Making it so that all objects accelerate at the same rate. So that was my answer for number 2. Number 3, using Newton's third law, so this is the law of action and reaction forces, describe the horizontal forces involved in walking forwards. What forces need to be considered? Does one force cause another force? So those last 2 questions are just extensions to clarify what I was asking for in this problem. Did not have to answer them explicitly, but if you answered them, then you pretty much answer the whole point of the question anyway. So that's why those exist. That's why those were there. So horizontal forces involved in walking. The reason I say that is because, of course, there are tons and tons of forces. Every individual muscle fiber and piece of your body is involved in when you walk. I don't even want to pretend I understand the biomechanics of all that. But what I do understand is the little bit of friction between your feet and the floor. So to walk, you push backwards on the ground. And this is an action force. Then the ground pushes forwards, so the opposite direction, on you with friction. This is the reaction force. And it is also static friction. Assuming that your feet do not slip. And those are the horizontal forces. You push backwards on the ground with an action force. The equal and opposite reaction force is the force of friction of the ground pushing back on you. It's equal in magnitude, opposite in direction. You move because you have far less inertia than the planet. So you don't move the planet when you walk. The planet moves you. Hate to break it to you. We can't all be superheroes. Question 4. 2 astronauts in space are initially at rest relative to each other. Astronaut A has a mass of 75 kilograms. Astronaut B has a mass of 60 kilograms. Astronaut A pushes astronaut B. Compare the new velocities of the astronauts. So the initial velocities are both at rest. They're both 0. So now we have 2 different velocities. We're going to have velocity of A and velocity of B. Initially equals 0. After the push, they're not going to be 0. Now, I don't give you enough information to actually figure out what it is. Some of you went ahead and did some calculations with the mass, figuring out some ratios, and I think that was great. That was awesome. You didn't have to, but great job. We know that astronaut A weighs more. So we know that astronaut A has a larger inertia. It's more difficult to accelerate them. So we know that VAF has to be smaller than VBF. And we are talking about the absolute values here. This is because astronaut A has a larger moment of inertia. Now, getting back to what I was first writing over here, the two equations I didn't finish, VAF is going to equal some speed in the, let's say, left direction. VBF is going to equal some other speed. Let's call that velocity 2. I'll call the other one velocity 1. In the right direction. Let's say that A gets pushed to the left, B gets pushed to the right. And the directions have to be opposite. So opposite directions because of the action and reaction forces having opposite directions. So this question was a combination of Newton's first and third laws. Question 2 was Newton's, that's an R, was Newton's first law. Question 3 was Newton's third law. 4 was Newton's first law and Newton's third law. So some concept questions, 2, 3, and 4. Question 5. A person is pushing a 20-kilogram lawnmower across the level ground by applying a force of 50 newtons. That makes an angle of 30 degrees above the horizontal. The coefficient of kinetic friction between the lawnmower and the grass is 0.25. Use significant figures in your answer for this problem. I'm going to tackle that first, actually. Now, the number of significant figures that you use in your final answer is equal to the least precise number given to you. So, looking at the numbers given to us in the question, we have 20.0, so 20.0 kilograms. It's 3 significant figures. Reading further on, we have 50.0 newtons. That's again 3 significant figures. And then, 30 degrees above the horizontal. That is 1 significant figure. We do not have a decimal point. We do not have a 0 after the decimal point. That's nothing. So that's just 1 significant figure. Reading on further, the last number we're given is 0.25. That's 2 significant figures. So we need to round our final answer to 1 sig fig. I will keep that in the back pocket for now. Let's look at part A. Draw a free body diagram of the problem. 2 points. So start with a box, trusty box. You did not have to do this part, but I do like writing the mass inside the box. I don't know why. I don't know what made me start doing that. I just like doing it. So I have an applied force acting above the horizontal at an angle of 30 degrees. And it has a magnitude of 50 newtons, but I don't need to do that. I don't need to write that for now. That's my applied force. My force of friction is going to act in the opposite direction. It is in motion, so this is kinetic friction. I'm also just told it's kinetic friction in the problem. And I still have a normal force and force of gravity. So that was everything I was looking for in the free body diagram. And we're asked to find the acceleration of the lawnmower. So to find the acceleration, we know we're going to need to find the F net and divide it by the mass of the lawnmower. And that will give us our acceleration. Now, I'm going to solve this problem a little bit differently than I normally would, and I'm hopefully going to make this make sense. So normally I'd go and I'd find everything individually by itself, But I'm going to show a way to turn this into just one single equation that you punch into your calculator. I'll show how I built it. This is how I would solve this problem as well. This isn't just me breaking it down or doing it in a special way because I think it looks better. This is how I would actually solve it. So I would continue this, and I would say, I'd set m aside for now, because I know what the mass is. I can leave that for last. F net. I know that this is only going to accelerate in the horizontal direction, not the y direction. So what I'm actually looking for is F net x over m. And F net x, this is just going to be the sum of all of the forces in the f direction, or in the x direction. So that's going to be the x component of the applied force plus the force of friction divided by mass. Now, for some subbing in, and this is where it might get a little complicated. FAX. Now, our applied force acts on an angle of 30 degrees. We're looking for the x component that is adjacent. So that is going to be FA times the cosine of theta, where theta is 30 degrees. Good so far. Now, these forces act in opposite directions. So I'm not going to be adding them. I'm going to have to subtract them. And I know that the force of friction is equal to the coefficient of friction times the normal force. Expanding further, well, what's the normal force? I still have everything else that's the same. And I'm going to plug in all my numbers at the end. Everything else up until the normal force is the same. I'm going to put some brackets here. So our normal force. This force is going to be what balances the force of gravity and the vertical components of the applied force. So part of the applied force is being pushed straight down. So to balance this out, the normal force is balancing the y component of the applied force and the force of gravity. It has to balance both. So in this bracket here, I need both of those forces. So first, I'll do force of gravity. So mg. I'll just write the force of gravity for now. Force of gravity plus Fay. Again, I'll divide by mass. And getting close to the end here, I have Fa cos theta minus mu k times mg, and this is plus Fa sine theta all over m. Now this is Fa sine theta because the y component is opposite of that 30-degree angle back in our free body diagram. And now we have everything in here. We have Fa, we have theta, we have mu k, we have m, we know g is 9.8. And that's everything we need. We've been given everything. So now we can actually go ahead and plug some numbers in. So we have 50 cosine of 30 degrees minus 0.25 times, this is 20 times 9.8 plus 50 sine 30, which that whole thing is just 25, all over 20. Acceleration, you should get negative 0.6 meters per second squared. And looking back, this is, in fact, 1 sig fig, one significant figure. It is the same. So that is how I solve this problem. I like to put everything in general into one big equation and punch it in my calculator. Do I think it's the best method? Probably not. It's definitely leaves you open to make mistakes, but if you're careful with it, take your time, be careful with your brackets. It is a good way to do it, I think. I like working in general, plugging my numbers right at the end. So that's a solution method I don't normally show you guys, but I think it would be good for you to see. I think me explaining as it goes through, you can rewind if need be, will help. Otherwise, please ask me in person. I'd be glad to show you how to solve this without putting it all into one big giant equation, solving it separately. So I'd be glad to show you how to do that as well. But for now, moving on. Number 6. A 5 kilogram block rests on a 25-degree incline. I'm going to start by drawing a diagram right away. So this is 25 degrees. I got a block. It's 5 kilograms. I know I have a normal force here. The coefficient of static friction between the block and the surface is 0.45. So I have static friction. There's no other force, so I know static friction is going to be pointing up the ramp. And the force of gravity is going to be pulling it down. And that's all my forces. Right. Just showing that I can break that up in components because I think I have to do that later. Will the block slide down the incline or will it be held in place by friction? So basically we need to see is FGX larger than FS? That's what we need to find. We need to figure out which one's larger. So let's start by finding FGX. I know that FGX is going to be equal to FG sine theta, because the angles here are equal, and that's going to be mg sine theta, which gives us 5 times 9.8 times the sine of 25, and that gives us about 20.71 newtons. Great. So now let's find the force of static friction. To do that, I need to find the normal force. To do that, I need to find the y component of the force of gravity. So I will do all this in a different color. So I need FGY equals FG cos theta equals mg cos theta equals 5 times 9.8 cos 25 and 5.98 cos 25. I do not have that written down, so let me grab my calculator quickly. I had everything else written down except for that, apparently. 5 times 9.8 times the cosine of 25. And this is 44.41 for FGY. Now, FGY is the only the only force in the y direction that's pointing downwards. The only one pointing upwards is the normal force. So this means that the magnitude of the normal force is equal to the magnitude of FGY. So I can say that the normal force is equal to 44.41 newtons in the positive y direction. And the force of static friction is equal to the coefficient of static friction times the magnitude of the normal force. And that's going to be equal to 0.45 times 44.41. And I did already have the final answer written down. I had 19.98 newtons for the force of static friction. So that tells us here that FGX is larger than FS, and therefore the block slides down the ramp and that is the answer for number 6. I thought putting number 7 in here would be a nice little break. Short little break. For each scenario, determine if static friction or kinetic friction is involved. Part A, hockey pucks sliding across ice. It is sliding, it's moving, so this is kinetic. The friction between a person, part B, the friction between a person's shoes and a running track as they run around it. The person's feet are not slipping as they run around it, so this is static. Car tires on the road while driving normally. This is static. In normal driving conditions, your tires are not squealing, you're not sliding. And part D, car tires in the road while sliding to stop on ice. This is where we are sliding, so this is kinetic. Just simple one-word answers. Now, there was one quick thing about my wording here. I just asked you to determine if either of the forces of either of the types of friction are involved. Technically, you could have just written the word yes for all 4 parts and been correct. One person did that. You're right. That's on me for not wording this correctly. So, good job finding a loophole, I guess. But what I was looking for is kinetic, static, static, kinetic. Last question, the big one here. A 2-kilogram projectile is pushed up a 30-degree ramp by a constant applied force of 90 newtons directed parallel to the incline. The coefficient of kinetic friction between the projectile and the ramp is 0.2. Again, this is kinetic, so it is moving. The projectile travels 0.6 meters along the ramp before leaving the edge and then follows normal projectile motion through the air. It lands at the same height it was launched from. So that will come into play later on. What I want you to do is find the horizontal distance that the projectile travels. A little bit of a hint, you must use forces and then kinematics, specifically in that order. So, lots of words. Let's make a drawing. Figure out what's going on here. 2 kilograms. Force of gravity going down. We know it's going to have components. We know we have an applied force pushing up the ramp. We know we have a normal force, perpendicular. And we know friction opposes motion. So that's going to point backwards. So that is a little free body diagram. Help us keep track of what is going on. Here we got FGX. Here we got FGY. So we have 3 forces in the horizontal direction, FA, FK, and FGX. 2 forces in the vertical direction, FN and FGY. Whew, lots of words. So I know I want horizontal distance projectile travels, and I know I was told that it lands at the same height it was launched from. This tells me, both of these things tell me that I want to use my horizontal range equation. This one right in the middle. So, x equals vi squared sine 2 theta I over g. I know I want to use that equation. To do that, I need theta, which I'm given, that's 30 degrees. And in here's also 30 degrees. I'll mark that while I'm at it. I know g. I need initial velocity here. I need to find my initial velocity. Well, to get that, I'm going to need to know the acceleration of this projectile. I'm going to need to know what the final speed is when it leaves the ramp after it's done accelerating. So to find acceleration, I know I'm going to need net force, because F net equals ma, a equals F net x over m. We're looking at F net x because that is what is parallel to the velocity. The perpendicular forces are not going to matter here. It's not crashing through the bottom of the ramp. It's not hopping off the ramp before it reaches the end. It's not moving vertically at all. So we only care about F net x. And F net x is going to be the sum of all the forces in the x direction. So this is going to be Fk plus Fgx plus Fa. So let's find them. Let's go find those first. So Fk, let's find them in order. This is going to be the coefficient of kinetic friction times the normal force. And in this case, the normal force is going to be balancing the y component of the force of gravity. So that is Fgy. So this is going to be mu k equals mg cos theta. So Fk there we go. Subbing in numbers, what is our coefficient? 0.2. That's what it was. So 0.2 times 2 times 9.8 cosine of 30 degrees. And our Fk is equal to 3.39 newtons. That was the big one there. Fgx is going to be very, very, very similar to Fgy. So this is our Fg sine theta, again, because of how we break down the components. So this is going to be mg sine theta equals 2 times 9.8 times the sine of 30. The sine of 30 is actually 1/2, so the 1/2 and the 2, so the 2 and the sine 30 cancel out. So this is just going to be 9.8 newtons. So Fgx is 9.8 newtons. I'm going to add some directions here. These are both down the ramp. And then Fa is, we are told it is 90 newtons up the ramp. I'm going to say that these two directions are positive, which means that when I plug in these numbers, Fk is going to be negative 3.39 minus 9.8 plus 90. That gives us F net x equal to 76.81 newtons up the ramp. Acceleration is F net x over m. And that is going to be our 76.81 that we just calculated over 2. So our acceleration is 38.405 meters per second squared. Again, this is up the ramp. And now we have our acceleration. So we are done with the forces part of this. Now we can solve for it's the final velocity here. So we are going to say that this starts at rest. So we are going to say that VI equals 0. VF is what we're looking for. VF is the final velocity after it accelerates as it's leaving the ramp. And we know what the acceleration is. We just calculated that, 38.405 meters per second squared. And we know delta D, that is 0.6 meters, given to us in the beginning of the question. I'm going to use one of our kinematic equations, VF squared equals VI squared plus 2a delta D. This means that VF is equal to the square root of 2a delta D, because VI is equal to 0, so we cancel that out. So VF equals the square root of 2 times 38.405 times 0.6. Final velocity is 6.79 meters per second. And this final velocity here, this is the launch velocity. So now this is VI. So this is our initial launch velocity. So for our range, VI squared sine 2 theta I over G gives us our final answer here. So we're going to have, that squared is nowhere near where squared should be. There we go. So I'm going to have 6.79 squared sine 2 times 30 over 9.8. Punching this into a calculator gives us 4.1 meters. And that is our final answer. I asked for horizontal range. It's not a vector, it's just a scalar. And that was the problem. Took a while, took a lot of work, but we got there. And that was it for assignment 7. There was nothing else. Again, if you have any questions about how to solve question 5 here, how I solved it all in one step, please let me know. It was very, very similar to how I broke down the forces in questions 6 and 8 immediately afterwards. Very, very similar to how that is done. Please take a look at those two first. If you're still not confused, please ask me. I do have time to help you out. I'd be happy to help. So let me know, email me, talk to me after class, whatever works best. Thank you for watching.